is our student Michael Hua from University of Michigan on non-destructive assay of Neptune-237. Please go ahead, Michael, if you are ready.
Yeah, sharing the screen now. All right. Thank you, Professor He, for the introduction. And like Professor said, yeah, I'll be talking about the non-destructive assay of Neptunium-237. And Neptunium-237 is a potentially weapons-usable isotope. The US Department of Energy classifies it as other nuclear material, so not quite special nuclear material, but pretty close. It's subject to the same safeguards as uranium-235 and reportable in gram quantities. A lot of it is produced. 3,000 kilograms is annually produced, and you only need 40 to 60 kilograms for a bare sphere critical mass. So there's definitely enough material to make a weapon. The international community recognizes the possibility of a Neptunium-237 based weapon, and they point out that characteristics that normally make isotopes undesirable for weapons, such as self-protecting dose rate, heat generation, spontaneous fission, are not present in Neptunium-237. There are also commercial applications for Neptunium-237. So plutonium-238 is an isotope that powers RTGs for space applications, and you produce plutonium-238 by using Neptunium-237 as a target and bombarding it. So Neptunium-237 could be dangerous. It is a proliferation concern, but yet we don't have the capacity to efficiently and effectively assay Neptunium-237. So it's a missing piece of our safeguards toolbox. So our goal is to develop such a system, and the goal of the system is to be able to verify or measure the mass of an unknown sample in a reasonable amount of time. We're talking order of minutes. That's on the right side of the screen. That's me holding the Neptunium sphere at the DAF, and we'll talk about that soon. Developing a Neptunium-230 assay system is critical to NNSA's mission. I grabbed these quotes from the website and have just kind of highlighted parts from each of the mission areas. So under material management and minimization, the most difficult step in producing a weapon is obtaining the material. So we want to be able to safeguard. Within global material insecurity, same thing. We want to prevent terrorists from acquiring this material. Non-proliferation, we want to prevent the proliferation, and research and development. We want to be able to detect and monitor foreign nuclear fuel cycles and weapons development. And we can't do that if we can't measure Neptunium. So we need a way to do this, and it's not as simple as just going in and weighing it, because how do we know it's Neptunium? How do we know it's not just a sphere of lead? So we need to use something that's unique to the Neptunium. So what we're going to do is exploit the signature of fission. When an isotope fissions, as shown in the animation to the top right, multiplets of neutrons are emitted. These are correlated in time, and the number that are emitted is completely random. However, over many, many fissions, they start to follow a distribution, as shown in the lower left. So the multiplicity on the bottom, so 2 would correspond to the double multiplicity. And what we can do is measure the doubles and triples on neutron multiplicity count rates, and then use calibration curves to determine the mass of the sample. So in general, the higher your doubles rate, the higher your triples rate, so the higher number of correlated neutrons you're counting, the more mass there is. The neutrons, or the way that this typically works, is we would put a sample between many, many detectors, and then each of these detectors would count neutrons. And this is typically done with helium-3 detectors. For other isotopes, but these helium-3 systems currently don't work. So the approach that we use is called neutron multiplicity counting. And what we do in a measurement is we log the time of neutron detections. So this is also known as list mode data. But what we're really getting is a list of times denoted on this timeline, and each of these blocks is a detection. What we then do is look in small instances of time denoted by this red box, and count the number of neutrons in this small interval. So in this case, this is 3, 2, 1, 3, and then we use something called factorial moment counting to turn these observations into those doubles and triples multiplicity count rates. And they just correct for things such as accidentals, and the possibility that maybe this triple is really a double and a single. So we use factorial moment counting to get to that doubles and triples multiplicity count rate. So what we're going to do in this presentation and in this study is compare helium-3, which I've already claimed doesn't work, to organic scintillators, and hopefully we will discover a working system with the organics. So background on the helium-3. Helium-3 detectors are thermal neutron capture based. So we take fast neutrons from fission, so in the MeV range, and moderate them to thermal, so 0.025 eV, before they're captured in the helium-3 detector. So in this rendering, this is a rendering of the epithermal neutron multiplicity counter, which has 121 helium-3 detectors. The space in between would be filled with polyethylene, and the neutrons coming from the source would bounce around in the polyethylene and eventually get detected in the tube. This process of moderation takes some time, and it's on the microsecond scale. So we think of helium-3 systems as microsecond. Organic scintillators, on the other hand, which we've heard a lot about over the past few days of the symposium, detect neutrons via elastic scatter. So we don't need the moderation, and we detect them directly. And the time scale of organic scintillators is nanosecond or faster. So Will and Nathan's system is hundreds of picoseconds. The systems that you're going to see today on this talk are nanosecond. So what we're going to do in the simulation study is kind of compare our ability to discern different masses. And we're going to do that by simulating 20 masses logarithmically spaced between 10 and 1 kilogram. Sorry, 10 grams and 1 kilogram. The reason that I choose logarithmic spacing is that to distinguish any two subsequent masses, you need 12% relative uncertainty to differentiate them. So we'll just jump into the results. So on the left, left in blue, we see organic scintillator data. On the right, in red, you see helium-3 data. On the top, we look at the doubles multiplicity count rate. On the bottom, we look at the triples multiplicity count rate. For the doubles, for the organic scintillator, the error bars, they're there, but they're smaller than the marker. Whereas for helium-3, for large masses, we can distinguish them. The markers are, so the error bars are smaller than the markers. But when we zoom into very small masses, there's some overlap. We observe similar things with the triples rate. They're just rare, and you have another efficiency term for detecting another neutron. So the statistics aren't as good. But still, I forgot to say, we simulated a 20-minute measurement. In 20 minutes, the organic scintillator system can distinguish all these different masses. Whereas for the helium-3, it's abysmal. You can't tell 10 grams apart from 1 kilogram. So in 20 minutes, organic scintillators can do it. If we assume that this uncertainty is completely statistics, it would take the helium-3 system 6 days. So that's prohibitive. You can't go into a facility and measure. You can't spend a week measuring all of the neptunium samples. And even then, it's not really feasible to pick a subset and hope that that random subset is representative. Whereas 20 minutes is something that we could work with. Or if we only wanted to measure the doubles and work with the doubles, even less time. So this is simulation world, where we showed that organics work better, but what about in a real measurement? So we went ahead and at the National Criticality Experiments Research Center located within the device assembly facility, we measured a 6 kilogram sphere of neptunium-237. We used two systems, a helium-3 system called the Nomad, which is 15 helium-3 tubes embedded in polyethylene. And then we used a prototype organic scintillator array, so 12 transdoping organic scintillator crystals. A photo of the measurement setup is shown on the right. So we have helium-3 detectors across from each other, organic scintillator detectors across from each other, that tin copper shielding that Noah was talking about in his presentation, and then the neptunium sits inside this nickel reflector. And neptunium is stable. It has a half-life in the billions of years. So we have to induce fission, and we do that with an americium beryllium source. And we'll go ahead and look at the results. So what we're plotting here is the relative uncertainty in the doubles multiplicity count rate. Just looking at some numbers first before really diving in. To achieve 1% relative uncertainty in the doubles multiplicity rate, it takes organic scintillation less than 5 minutes, whereas for the helium-3 system, it would take 2 days. Maybe relaxing these requirements and only going for 10% relative uncertainty, the organic scintillator system can do it in less than 3 seconds, whereas the helium-3 system would take 30 minutes. We do fit these curves with, we show that the curves fall off as 1 over root measurement time, which kind of shows that at least in this regime, the dominant form of uncertainty is coming from statistics. Of course, there could be some systematic asymptote at large times that we can't beat. This may be surprising because helium-3 detectors are more efficient than organic scintillators. In this case, they are 13.7 times more efficient based on total neutron count. Organic scintillators, on the other hand, we're taking that same measurement time from several slides ago, and we're dividing it into those red windows. The helium-3 system, we said, was microsecond, and actually, in this application, it was 1 millisecond. So we took that total time and divided it into millisecond chunks, whereas the organic scintillator data was divided into 100 nanosecond counts. So even though the helium-3 system has more neutron counts, the organic scintillator has 10 to the 4 more gates, more observation windows. And that's where the statistics come in. So if we take the number of gates and divide by the total neutron efficiency, it comes out to a number like 700, so 10 to the 2, and that's about the factor of difference that we see between these curves. So why do organic scintillators do well? Superior timing capabilities, which help with the statistics. So the conclusions here, at least for IAEA applications, helium-3 should be replaced with organic scintillators for the assay of neptunium-237. And if we're going to get this much precision in these measurements, maybe for uranium and plutonium as well. In the measured comparison, we show that the organics are relatively better than the helium-3. But in an absolute sense, the organics really open the doors for other possibilities. If we can achieve 10% relative uncertainty in less than 3 seconds, maybe we can look at new applications such as measuring material in a pipe. So as we can affix this array around the pipe and measure material as it flows, and we can do dynamic assays or apply this to production facilities or, if needed, reactor pipes. Hopefully not, but if needed, we could. So the future work here is run some simulations and really test, can we do this with pipes? Kind of going back to Jawad's presentation last Tuesday, I believe, we also want to investigate limits by investigating bulk samples. So does our theory where we assume point kinetics break down? And do we need to do something a little bit more complex? And then also, these are organic scintillators where we detect both neutrons and photons with the same system. And we get way more photons than neutrons. So can we turn the photons into a signature? And theory has been developed for this, but we haven't tested it with measurement yet. The expected impact, these are all links, so you could download the slides, and these are links to papers or news releases. And a lot of the work done in our group, so this would be seminal research, gets transitioned into a deployed system. So we've done research before, and it's become a neutron collar for fresh fuel assay, which was built, tested, and deployed internationally. So my expected impact for this is truly when I say organic scintillators should replace helium-3, I expect that organic scintillators will replace helium-3 in these non-destructive assays. The MTV Impact has really enabled the collaboration to go and measure at the device assembly facility, NSERC at the device assembly facility. And it also has enabled collaborations with Los Alamos National Lab. And we're hoping to develop more collaboration with Y12 or Savannah River National Laboratory on this pipe application. with that, I'd like to acknowledge NNSA and DOE for funding the MTV and therein this work, and open it up to questions.
Thank you, Michael. That was a very good presentation. I see some questions posted on the chat. The first one asks you, do you have a preference? What type of organic scintillators you would choose to build organic scintillator-based neutron multiplicity counter? And for what reasons? Yeah.
Sure. If I don't have a budget, then maybe I would pick Stillbean. Stillbean's great. The reason that I like Stillbean so much is this pole shape discrimination is phenomenal. We can really separate the neutrons and photons very well. And this overlap, which does introduce systematic uncertainty, is very, very small. So I probably would pick Stillbean. If I'm thinking about rugged application, or if I want a cheaper system, then maybe I look at Nathan's organic class, which offers both better time resolution and energy resolution at the cost of poor pole shape discrimination, at least in its current state. If I'm looking for something cheap and effective, then I might go with liquid scintillators with EJ309.
Thank you. The next question is that have you considered the effects of having other actinide content mixed with the Neptunium-237? What's their effects?
Yeah, that's a really fair question. So the Neptunium sphere, when it was cast, so a few things, it was allowed to settle. So the isotopes split based on mass, and they broke off a piece to do some chemical analysis. But that chemical analysis isn't completely descriptive, and my LANO collaborators believe that there is some curium content inside the Nep sphere. The implication is that curium has a very high specific fission rate, specific spontaneous fission rate. There's also plutonium-240 in there. So there's a chance that we're accidentally assaying plutonium-240 and curium and not the neptunium, but we won't be able to tell until more chemical analysis is done.
Thank you. Are there other questions from the audience? If not, I have one general question for you, Michael. So you showed that the different result using helium-3 and these organic scintillators, the improvement is dramatic, very, very significant. So I was thinking, what is the fundamental difference? Say you could use the same similar neutron multiplicity counters on plutonium. And I forgot the difference between the organic-based system and the helium-3 based. I don't remember that dramatic difference between. So what really differentiates between the plutonium neutron multiplicity counter and these for the Neptunium-237? What made them different?
Yeah, I think there are a few things. The first is that Neptunium, induced fission in Neptunium is like a threshold interaction where you have to get above 800 keV. And because, so the reason that we're using americium beryllium and not americium lithium is that the mean energy of an americium beryllium neutron is 5 MeV, whereas for americium lithium, it's something like 600 keV. I might be getting my numbers a little bit off. But the higher energy you need more time for the neutrons to moderate inside the polyethylene. And so there's a larger smearing term in the helium-3 data. There's also, with the helium-3, sorry, I have to minimize the webcam for a second. The americium beryllium has a small end-to-end reaction possibility. But because of the smearing inside of the helium-3 system, whereas the doubles rate decays to 0 in the case of organic scintillators, that's not the case for helium-3. There's an asymptote due to accidentals. So I think the accidental rate in the case of Neptunium, based on the interrogation source, also differentiates the systems. Also differentiates it from plutonium.
Thank you. That's very good. So are there other questions? People can speak up on your microphone if you want. If not, let's move on to the next student.